Okay, today we see lecture 40 on embedded maximality by Harvey Friedman, please.
Thank you. So I made a lot of progress in cleaning up and perfecting the details here. I didn't quite finish, but you'll see went a long way, and we're going to go pretty quickly because a lot of it is stuff we already talked about. But this is kind of a more advanced state. There were some issues about how to exposit this. Uh, uh, because of repetition of arguments in slightly different contexts. And I think I got a good handle on that. So let's go through this. No change in my concept of the book. Um, I'm very anxious after this chapter, which is coming to a close. This has long been done. This is not changing. I mean, I'll have to. I might there might be have to be some minor changes in the introduction to this because to link up with the terminology in here, but it's minor. I want to get back into this because I left it in a promising state and I didn't get a chance to finish this, so I want to get to that. But anyways, you can see this chapter has gotten looks like it's gotten enlarged, which is not quite true. It's just the table of contents. Some of the sections now are very short. Uh, so we have this is background. This is all background. Uh, and this is where the thing really gets going. And this is a simple result from Ramsey's theorem in here, which we talked about last time. We talked about this last time. This is the complete characterization of one usability. This is we talk about this too. This is stability of usability, like closure under composition and inverse, some simple things. We have the two fundamental necessary conditions, um, and uh, we have this is kind of easy to prove, obvious. Uh, and then we have this chapter, which has remained unchanged for a long time, that completely characterizes which finite functions are usable. Which finite functions are usable goes all the way down here. And that's all done in CFA, super exponential function arithmetic, because that's where Ramsey's theorem sort of lives. So this is all been constant, no change. And then this is where we really start. And there's been some less is more stuff. In other words, there's some less stuff and better stuff, slightly simpler stuff. It looks like it's really very permanent now. The way I do this, we start with this. Um, yeah, sweet. And then one dimension and length one, so to speak, is uh, trivial. These are trivial when you have ones in here. Uh, this is the first term is the dimension. The second is the size of the field of the function. Okay, we'll go with that. I decided that I would have a single big section, and this is related to not repeating stuff endlessly. A single big section. Whoops, it's 3-8, not 3-6. 3-8. Single big section I show earlier that with the primes, it's equivalent to without the primes. So this is the real thing. But the actual thing one actually does is with a prime, just a slight change. But the real statement is it's not O, by the way. It's I, identity. Yeah, I, not O. It used to be O. Yeah. So this takes care of the argument in many different in four different contexts. This takes care of what the argument looks like with it turns out with these two sections. These two sections are the ones that change according to the context. Okay, this will be all explained. And there are four contexts. This, and these two. This, and these two. And these two this has easy combinatorics. This has easy combinatorics. And this has trickier combinatorics. In other words, large cardinal combinatorics. And this has large cardinal combinatorics. Okay. And so that takes care of the IEU stuff. Then there's the weak IEU stuff. And I decided to start over. I have a whole section, just like I had with IEU. I have this whole section of commonality. But a lot of this is literally the same. So a lot of this is literally the same as what I do with IEU prime. So there's the repetition is not as extreme as it could be. And this is different. The field doesn't have zero. So we'll talk about that quite a bit. And then the combinatorics, instead of the large cardinal combinatorics, for the weak, W means weak. It's the iterated exponential cardinal combinatorics. In other words, 2 omega, 2 to the omega, 2 to the 2 to the omega, and so forth. It's that stuff. So all this stuff with the weak form is provable in Zermelo. Provable in Zermelo. And we have this is provable with this cardinal, which is just iterated on omega, and then take the next cardinal after it. That's what the plus sign means, next cardinal. And this is also, but this time it's with an N. Okay. And then if you combine these results and the other ones, you get that this is enough, a min of k minus 2, n minus 2 subtle cardinal, and this is enough, the iterated exponentiation minimum of k minus 2, n minus 2 times. All right. Now, that's all I got up to that. That's the bulk of it. There's something I want to do with joint usability that is kind of important. This is bookkeeping, actually literally stating what the exact formal systems for these positive results. Exact formal systems. I don't use words like using omega 1. I actually put down a system, stuff like that. Graphs and emulators, the graphs are for linking to the reversal. Because this statement is the statement that is reversed in the reversal chapter, and it involves graphs, ordered, variant, simple graph. And emulators is just another alternative, which is important. I use that for gifted high school in some baby case. So emulator is worth mentioning. Further investigations, what's usable? The functions I'm considering that are usable are very simple here. They're just a finite function union the identity on an interval. But what if you look at all the finite unions of of intervals and points. I mean, and a finite function union, an identity function on a union of intervals, not just one. This turns out to be much more difficult, and there's a lot of questions that I don't resolve here about that. So there's a lot of stuff in here there's a lot of stuff in here. Maybe that's not the only thing that's in there, but I mean, for example, I don't have any reversals except for the one giant reversal. I don't have reversals. I haven't really tried to do them, but I haven't tried seriously to do them. But I don't have. I'm not putting in the book any reversals uh, of fragments. So there's all that stuff. All right, so let's get into this now. So 3.2 and 3.3 are background material. Um, and note that in chapter 2, the previous chapter, um, that's the core math chapter. We did that's based on now I look at that as a chapter on embeddings without maximality. And this chapter begins with um, no embedding and maximality without embedding. And now we're into the real core of the book, which is embedding with maximality, or embedded maximality. So this is the background: maximal chains and relations, maximal chains in order invariant functions. All right, so finally we get to the non-background material, the real thing. All right, so embedded maximality extends. Should I call it section 3.3? Is that correct? What is section 3.3? No. Um, yeah, yeah, that's okay. Yeah. Embedded maximality extends section 3.3 by requiring that the maximal chain has a given embedding. In other words, embedded maximality. And we talked about this setup. You have a partial function. Uh, yeah. So we have our usual thing. So a partial function from -1, 1 into -1, 1. This is by convention one-dimensional animal. Is usable if and only if every order invariant relation on every -1, 1 to the k has an F embedded maximal chain. That's the definition of usable. Uh, we can, for more refinements, we can talk about K usable, which just means that the order invariant relation is on K fixed. See, before it was on all these, and here it's just on this one. Okay. All right. And the embedded maximality program is to determine the usable F. That's it. That's all it is uh, in this book, at least. And we've completed, and that's a little bit of a lie because I do venture into joint reusability. Joint embedded maximality would be to determine the usable F1 through Fm or F1 through Fr. And in that's discussed some in the section on further investigations, the last section. All right, we've completed this for finite F, and that's in 3.5. The proof lies squarely, it's in CIFA. The situation is radically different when we venture modestly beyond finite usability. So we always have this convention. And we have this most basic usability that I talked last time when you just have um, a strictly increasing finite function uh, from the open interval into the open interval. You can just use Ramsey's theorem. And if the endpoints are also fixed, the same argument will work. Now, it's actually true that if F merely fixes one endpoint, it fixes just one endpoint, and I don't care whether it's even defined or fixing the other endpoint, then that's also usable if the function is finite. And that's harder. That's a special case of the serious theorem about that characterizes the finite usable functions. The one usable case, no matter whether the function is finite or infinite, is handled easily and by this theorem. And there's some closure properties and related properties that usability has. And then we have the two necessary conditions, even if the function is infinite. We have two necessary conditions. They're not sufficient. Okay, we have two necessary conditions. One is strictly increasing, and the other is a strict here. That you don't have a certain pattern. Okay. Where you don't have this, my finger going up, my finger going from this to this, and my finger going from this to this. That's what that is. All right. If F is too usable, it's strictly increasing, and if F is too usable, this holds. You can also drop dimension. These are all simple to do. Then we have the finite usability situation, and that's those are equivalent. And we actually have this cute statement that if finite F is usable if and only if every two element restriction is too usable. All right, so now we get into what's really going on in this book. Okay, so IEU, the identity extension usability theorem. If strictly increasing F contained in 0, 1 closed squared is finite, think of F as a set of ordered pairs. If strictly increasing F contained in closed interval 0, 1 squared is finite, then F union the identity function on -1 to 0 right open is usable. All right. Now, by the way, look at this statement. Strictly increasing is necessary. And 0 can be replaced by any rational other than 0 or 1. Excuse me, other than -1 or 1. And you can see that by isomorphism. In other words, this is an order theoretic situation, and we use 0. Well, that's the same as using any or all rationals strictly between 0 and 1. Okay. We show that this statement is provably equivalent to con SRP over WKL naught. Yes. So we immediately run into ZFC incompleteness when we do this. Right. So this is all discussed many times. Now, there's a very pretty way to weaken the statement so it's provable. The weakened statement is WIEU, weak identity extension usability. If strictly increasing f contained in 0, 1. Notice the way that I did with ordered pairs. So let's back up for a second. I chose to write f contained in closed unit interval 0, 1 squared. Yeah, I think I repeated this statement just now. Yeah, right here. So you see the difference between these two statements. The weaker one has 0 next to an open parenthesis. And in the other one, we just have 0 in a closed bracket. Oh, this is not right. Sorry. The official state, they're all equivalent, but the official statement is literally the same as this, except the zeros changed. And I do want to, it's, you can keep the 1. Yeah. Okay. These are the lead statements of embedded maximality, these two. So what we really are doing is just removing the singularity that's possible here with a 0. This causes a catastrophic drop in strength, and we can prove the weak form in ZC, well, or maybe, why don't I say Z? Okay, so let's see here. Yeah, and I conjecture that iterating the power set infinitely many times on omega is needed to prove WIEU, but that's a reversal and beyond the scope of the book. All right. So now I actually have calibration. This is the calibrated form. In other words, the dimension is fixed. Whoops, that should be K. The dimension is fixed, and the size of the field is fixed. See, that's what this is. And we can also calibrate WIEU, which is done right this time, except that should be K. Okay. So those are the main events. The two lead statements, IEU and WIEU, and their calibration via parameters. And then there's a couple of different forms that I really, the ones that I really are more convenient to actually work with. And I prove they're equivalent. So here's one for the IEU side. Here's one for the WIEU side. If strictly increasing F has the field explicitly given here, then F union the identity function on -1, 0 is usable, K usable. And the same thing over here. If strictly increasing F has field F equal 1 over n to n over n, these are entities. Then the identity F union the identity from -1, 0 is K usable. Okay, that's what we actually do. All right, these are the least statements of embedded maximality. The calibrated least statements are IEU, WIEU, with the parameters put in. The OE prime of KN and the WIE, I. Oh, there's a prime. These are the technical variants that we actually prove, right? This is what we actually prove. The equivalence is proved right here. See, this is equivalent to the thing with the primes. Okay. This is background material that's been constant for quite a while. This is also background material that's been constant for a while. Now we have two trivialities, dimension one and size of the field one. And right. So yeah, so this is a triviality. Okay, now this here is the section, as I stated earlier, in order to pick out the common core of the four sections that do those particular proofs. So we start with an order invariant relation, and the field is given this way, and F is strictly increasing. We want to prove that there exists an F-embedded maximal chain in R. The proof uses a suitably chosen uncountable regular cardinal kappa based on K and N. The proof is completed in these four sections using various combinatorics on kappa. So when the dimension is 2, for example, we show that kappa equals omega 1 suffices. Or when the function has a field of cardinality 2, it suffices to have an n minus 2, also suffices to have just omega 1. In both these cases, just omega 1. So that means that it's all well within ZF. Okay. So then I list okay, so here's the common part of the four proofs without the combinatorics. All right, let's see. All right, we've done this many times. We immediately go to this transfinite space. It has an obvious ordering less than star, which keeps it dense with endpoints. It has a well ordering that we need to do the transfinite recursion, less than double star, and then this is extended to dimension K. That's where we actually use we have to extend it to dimension K in order to do the transfinite recursion properly. Okay, and less than prime is any effective ordering on Q of type omega and left endpoint 0. Okay. So here's the less than star ordering, which is just lexicographic. And the double star ordering is lexicographic on pairs, uh, alpha P, beta Q. We've been over this a lot. Uh, and then and then we extend this to k dimensions canonically. It might be called the Lex Max. And then we have a summary of the major features of the orderings. Dense without left endpoint, and with the dense with the left and right endpoints is less than star. Less than double star is a well ordering on W, and less than W star K is a well ordering on W to the K. And then we define W. Yeah. All right. So in particular, W is W of kappa. And then next thing we do is we define this transfinitely greedy uh, maximal chain, ICH, inductive chain. In other words, we're basically lifting everything to the transfinite into this space. Here, this is a lifting. This is read less than star order equivalent, less than star order equivalent. So we're speaking of X and Y being less than star order equivalent. Some trivialities about R star. R star is a less than star OE invariant relation on W to the K. In that this R star is a less than star order invariant subset of W to the 2K, right? Because W star is a set of ordered pairs. So ICH R star is well defined as follows. X in WK lies in ICH of R star if and only if when you tack it on, it remains a chain. All right, so ICH of R star is uniquely defined. It's a maximal chain. And when you cut it off at any place, it's maximal in that place. That's because it's constructed greedily. Same thing. Okay, now we build this closed unbounded set. That's important. This cuts down, by the way, this is useful for cutting down the dimension K by 1. If I didn't put this in, I would still have all the good results for the elite statements, but I would be missing the sharpest form of what I know how to do when we actually have N or K fixed. So this is well worth doing, introducing this set E. It's a closed unbounded set. And here it is, of limit ordinals, such that the structures W alpha with alpha 0 replaced by kappa 0, this top point, Um, and let's see, there are two structures here. W alpha union this. Yeah, I didn't say this right. Oh, yeah, no, I'm sorry. This is right. Such that this tower of structures are elementary chain, and they're all elementary substructures of the limit, which is just the full W. See, we're cutting back W alpha, but we're putting back the kappa zero, you see. So this forms an elementary tower. Okay, and this is done by standard argument that everybody does. And we fix that E, and we actually get the following corollary, immediate corollary about E. If alpha is an E, we get an isomorphism between the structure where we had kappa zero instead of alpha zero. Um, and the structure W alpha flat out this way, we get an isomorphism where the isomorphism is the identity on the little structure, and it sends kappa zero to alpha zero, which it sends this guy to this guy. And then you get an immediate corollary called E lifting, which says that uh, if Y is the result of replacing its highest element by uh, something bigger, um, by replacing max of less than star X in X by Y, this should be Y greater than Y greater star X. Yeah. Uh, yeah, Y be the result of replacing the max by a larger element of E. That's what I meant to say. Then X is in ICH of R star if and only if Y is in ICH of R star. In other words, you take all the maximum elements uh, that are in E. That's the assumption, the max is in E, and replace it by bigger element of E. It doesn't change the truth value, the membership in ICH R star. Okay, so and that's what is in common to all these arguments. And another thing we always do is we take the first omega elements of E, and actually we do some more combinatorial. These are chosen from the closed abundance set from E, but not necessarily arbitrarily, but they have to be picked according to the combinatorics of kappa. And then we form F star. This is a finite function. We form F star in the transfinite, in our transfinite lifting, but F star is a form of F. Remember, F is finite. F has field, has that special field explicitly, and we take F star to be just its transfinite lifting in the obvious sense, so that the F star is isomorphic to the F. I mean, the F lives in the rationals, and this F star lives in a transfinite extension. All right, so since F is strictly increasing, F star is strictly increasing. And then we show that ICH R star is an F star union ID, the identity, embedded maximal chain in R star. In other words, we do exactly what we want to do with finding embedded maximal chains. We do it in the transfinite because we have the large cardinal combinatorics. We couldn't do it in the countable, in the regular rationals right away, because we don't have that kind of combinatorics there. In order to get the combinatorics that we need, we have to go up to the transfinite setting. And this is done using whatever the combinatorics that's available for that particular application. Now, this is something here that we do no matter what. We form the structure M with the ingredients that we set up, and then we let M prime be any countable elementary substructure whatsoever. And then we have that F star will remain the same in the two structures. See, we have two structures here, 1, 2. But the F star remains the same, right? And then we just make an isomorphism. Well, first we prove that M prime is a countable dense linear ordering, which is obvious with these endpoints. Then we also have that M prime satisfies that ICH R star is what we want because it's true. And it's true in M, and M prime is an elementary substructure of M, so it satisfies the same sentences. And then we actually take M prime and throw it back into the rationals with our usual F. And so therefore we get the conclusion. I see. So it's isomorphic to something here, and we don't know what the S is. The S is going to be the image under this isomorphism of ICH of R star. That's what the S is going to be. And so now we have gotten the title of the next section. S is an F union identity, embedded maximal chain in R. Okay, so this is the general way this is done. So for a particular example, how do we get an F union identity embedded maximal chain in R? Oh, yeah, that's just summarizing what we just did. All right, now we move on to one of the applications, which is using omega 1. Omega 1 is a uncountable regular cardinals, and that's what we needed in order to do those constructions without the combinatorics. And now we can do this with omega 1. We're left with some combinatorics that's easily done by hand, relatively easily done by hand, with a little bit of familiarity about what omega 1 is like. Okay. So that takes care of the case where the dimension is 2. And now we take care of the case where the field has cardinality 2. And that is similarly done. Except here we only need 2 ordinals, lambda 0 and lambda 1. And lambda 0 is going to be mapped to a 0, and lambda 1 is going to be mapped to 1. Remember, the image goes from -1 up. Okay. We have this. Now, the next 2 cases involve the large cardinals. So we have this subtle cardinal combinatorics, which I talked about before. I think it was perfected up some. There's the standard large cardinal combinatorics, and then there's this made up one that's more specialized for our purposes. We have a bunch of functions on the less than or equal to k tuples from kappa into the subsets of kappa, and we also have a closed unbounded set C, sorry. And we claim there's an infinite V contained in C, such that for all order equivalent x and y, Fix intersect min of xy equals Fiy intersect min of xy. All right, but now this has an alternative form in which you have dimension k, but the field has cardinality n, and the tuples that you want to consider of length k have at most n terms, have at most n distinct terms. So if you put that additional kicker on this, you'll see that n subtle is enough. You don't need k subtle. You don't need k subtle. You just need n subtle. All right. Okay, then we handle this case, i.e. u prime of kn, with a k minus 2 subtle kappa. One of these should be a kappa. Let's see here. Here. All right, so this is the combinatorics needed to get closer to the result that the embedding condition that we seek. There's an infinite V contained in E such that the following holds. Let alpha and V be given, and I have U and V of this form, which are order equivalent in the transfinite setting, and assume U and V have all coordinates all low coordinates in the same positions, then there's at least one low coordinate. Then you get that U is in ICH if and only if V is in ICH. And this has an easy modification where you don't insist that there be at least one. And you go to an infinite subset of V. You use Ramsey's theorem for you use the ordinary infinite Ramsey's theorem in order to handle this V prime, so that we don't have to assume that there's at least one such coordinate. Yeah, we've been over this and in why in various contexts, this kind of idea. You get almost what you want, and then to finish it off to get exactly what you want, you use the infinite Ramsey's theorem to cut things back. Okay, and then we take the usual omega first omega elements, as we've done previously, and then we get that we get that we really do have an appropriate embedded maximal chain, and we're cutting everything back to lambda n minus one. Yeah, that's right. Okay, now we can do the same thing here, because we also had that variant in the we also had that variant previously, where we use the n instead of the k. So we're going to use n subtle here instead of k subtle. N minus 2, everything's minus 2. All right. So I know this is a little bit complicated, but it's pretty much have to do this. Just to give you a good idea. I think after next week, I will have a little bit more of this to finish up. Then there'll be a formal manuscript, so you can look at all the proofs in detail. There'll be a formal manuscript put on my website, wrapping this up. All right. So then we can do this without, we can also do this for the weak form, and that's the form when at least the prime form, the technical form, where the field is like this. So it's away from zero. The field is away from zero. And so we go through this. It's actually the same, except the combinatorics is different, is weaker, because we actually use the Erdős-Radó theorem is all we need. We don't need anything, any large cardinal. So this is all the same. Here's the combinatorics that we need. Yeah, so this is a statement of the Erdős-Radó theorem. I think this is essentially the form it takes in the paper, the well-known paper down here in 1956. If you use this combinatorics, you don't have to use the large cardinal combinatorics because you're away from that singularity. So you just have to carefully check that this is enough. And I do this pretty carefully right here. It's all very similar, but slightly different. Not much. See, we get this. And then we can consolidate everything with 318. They were actually using min of k minus 2, n minus 2 subtle to get IEU of kn. And to get WIEU of kn, we're using this cardinal, which is available in Z. All right, and that's the last thing here. We get everything is matching up nicely. All right, so I'm going to be polishing up and finishing off this chapter for sure for next week, and then we can move on to the finite forms and get this book finished up. This will be a. It has. I want it to be done right, readable and comprehensive within its own realm. I mean, there was not really much, not that much mission creep. Mission creep, I sort of put the dampers on at one point, and I think this is really the right scope of the book, with, of course, generous chapters about future investigations and so forth. All right, I think I'm done now. Thank you.